Hello and welcome back. In this lesson, you'll see beautiful examples of abstract art from Kenya. This is Chapter 5.5, Measures of Variability, and we'll be looking at closing thoughts. Our topics, in summary, for Chapter 5 were Unit 1, Range and Q, Unit 2, Variance and Standard Deviation, Unit 3, Linear Transformations, Unit 4, Other Properties of S, or Standard Deviation, and now we're on Unit 5, Closing Thoughts. Our topics for Unit 5.5 are the sum of squares, alternate computational formulas, and other measures of variability. Here is our formula for standard deviation. The number in the numerator is the sum of squared deviation scores, and this number is the star player in many statistics that we'll learn later in the course. This part of the formula is highlighted with a purple circle. We found this quantity the long way, but there is another quicker way to do it. Many statisticians use the shorthand label for the quantity, simply say sum of squares, but I prefer to use the longhand label, sum of squared deviations from the mean, at least for a while until that idea becomes second nature. In a prior lesson, we found the sum of squared deviations from the mean the long way. We literally found each person's deviation score by subtracting the mean from their score. We squared each of these values and then summed them. There are easier ways to find the sum of squared deviations from the mean. Here are two different formulas for the sum of squared deviations from the mean. These are called the raw score formulas for the sum of squared deviations from the mean. Notice the difference between the little x's and the big X's. The first formula asks that we sum each value of x, square that number, and divide by n. Then subtract this quantity from the first part of the formula, which we obtain by squaring each value of x and summing them. There is a second formula we can use to accomplish this same result, and it's written below the first one. It asks that we square each x value, take their mean, and multiply by n to get a number. Then subtract this number from another number derived by summing all the values of x squared. Here's our little 8-person data set. In the first column, with uppercase X as the heading, are the raw scores for each of the 8 people. The sum of these raw scores, as you can see at the bottom, is 32. We divide 32 by 8, which is the number of people in the sample, and find a mean of 4 for the raw scores. Then to get the deviation scores, we subtract 4 from each score. The deviation scores are listed in the center column. As a reminder about the notation, uppercase X stands for the raw score, lowercase x stands for the deviation scores. Then we square the deviation scores in the right column and then sum the squared deviation scores to get the answer, which is 28. This is the correct answer. This is the long version, the literal method for computing the sum of squared deviations from the mean, which is pretty easy for a small data set of 8 people, but becomes much more cumbersome with a large data set of, say, thousands of people. What we want to do is show how to get this correct answer using our alternative computation formulas that are quicker and simpler. For the first raw score formula, we need 2 ingredients: the sum of all the raw score values of x, which is 32, and the sum of the squared values of x, which is 156. Let's plug sum of squared raw scores, 156, into the first part of the formula, and sum of scores, 32, into the second part of the formula. Then we do the math by squaring the 32, dividing that number by 8, and subtracting the new number from 156, and we find the answer, 28, which is precisely the answer we got when we did the problem the long way. that is without this handy formula. Notice that summing the squared scores does not arrive at the same number as adding the numbers and then squaring. This is the sum of squares raw score formula 2. If we plug the ingredients into raw score formula number 2, we place 156 into the first part of the formula, plug in 8 for the sample size n, then plug in 4 for the mean of the raw scores and square the 4. Again, we arrive at the correct answer, 28. Our goal is simply to show that there are multiple paths to a correct result. You don't need to know these raw score formulas for this course. You just need to know how to compute the sum of squared deviations the long way. But it may be helpful for you to know these formulas in the future. We have other measures of variability. One is the decile deviation, symbolized as uppercase D, and that equals P90 minus P10. So we talked about alternative ways of finding central tendency, and so for purposes of parallel construction, we will also look at some alternatives for computing variability. We'll do this with the next set of slides. This is something people use from time to time, and it's called the decile deviation, and it's computed as the 90th percentile, or P sub 90, minus the 10th percentile, or P sub 10. This is comparable to the interquartile range we learned in a prior unit. Recall that quantity was the middle 50% of the data. This is the same concept, it's just a bigger bite out of the distribution, encompassing the middle 80% of the data. Admittedly, this method is much cruder than prior methods of computing variability. We lose a lot of information with the decile deviation method, but in some problems, a quick and simple measure of variability is okay. We can link this to our metaphor of statistical applications as abstract art. Sometimes a simple summary gives us the essential information we need. Here's another way of computing variability. Recall we talked earlier about finding a mean for the deviation scores, that is, a mean for each person's raw score, subtracting the mean for the sample. We found that if we simply added all these values together, we ended up with 0 because the negative values canceled out all the positive values. So we chose to solve this problem by squaring the deviation scores. But another way we could do this would be to take the absolute value of the deviation scores, find their average, and this would give us a mean deviation score symbolized as uppercase M, uppercase D, or MD. It's a very sensible thing to do and makes sense intuitively, but as I said before, when we take absolute values of numbers, we lose some helpful algebraic properties. So this statistic is not used very much, but some statisticians find it to be useful now and then. A third alternative measure of spread is the coefficient of variability. It involves the standard deviation, but it expresses it as a percentage of the mean. We want to cast the measure of variability in terms of the magnitude of where the data tend to reside. Suppose we had 3 people with incomes $5,000 apart. For example, person 1 had $10,000 income, person 2 had an income of $15,000, and person 3 had an income of $20,000. There's quite a psychic difference between people in each of these income groups. The person who makes $20,000 a year makes twice as much as the person who only makes $10,000 a year. Now, compare this to another group of people with incomes, again, $5,000 apart, but who are making a lot more money. Their incomes are $195,000, $200,000, and $205,000 a year. The spread of the data is the same as we saw with the 3 people in the prior example, but the $5,000 difference in income between each member of this group is marginal compared to the original example. For example, the $10,000 difference between the high and low person in this group is not felt as much in day-to-day expenses as the $10,000 difference between the people making much lower salaries of $10,000 to $20,000. The point of computing the coefficient of variability is to attempt to compare the differences $10,000 makes for these two sets of people, a high-income group and a low-income group. This is the end of Chapter 5. So let's turn to Chapter 6. The major topic in Chapter 6 is the normal distribution, and we'll be talking about computing standard scores and the shape of the distribution. If you're taking this course as a series of mini-courses, this lesson marks the end of mini-course number 1, in which we covered the purpose of statistics and descriptive methods in chapters 1 through 5. Next up is mini-course number 2, in which we'll cover the normal distribution, standard scores, and the bivariate normal distribution in chapters 6 and 7.